Hello, everybody. Give me 1 second here, and I'll start talking. I'm just checking something. All right. Hello, everybody. I'm just checking up on something here for next class, but then we'll get started. There's a few things, just two things actually, I want to talk about that are new. Okay. It's that one, isn't it? Yeah, okay. All right. Hello, everybody. Good morning. Welcome. Fuzzy, I had a good break. Obviously, I was not around very much, in case you didn't notice. But, yeah, I had a great break, but I am glad to be back. I've got Patty in the bag next to me, so that's always nice. Yong, Sito, Chef, and Topwolf, good to see you all. Thanks for coming today. Hope you guys had a good break. The Thanksgiving break is really kind of like, what the heck? Why is it so close to the end of the semester? I don't know. I feel like I say that every year. I don't know how I feel about it, because I was home with my parents and I couldn't bring myself to work on anything while I was there, and yet here I am now cramming for the end of the semester, as I'm sure many of you are too. Okay. Hello, Nick. Good to see you. Oh yeah, I tell you, I've got some big projects coming on. I've got some big projects coming up here. I've barely done anything on them. Yeah, and so your grades, obviously, I'm a little behind on those. Next week, those will all be coming. Those will all be coming in. I'm sorry about that, but for those of you who use the code grade, you'll see that you if you got 100 points, it's likely that you'll get 100% on those assignments. So code grade is a little helpful in that and telling you how you did. Obviously, if you didn't get a very good score on the code grade, I will be manually reviewing it. But like I said, I have some priorities that I'm taking care of right now. So I'm sorry about that, but I will have those coming in as soon as I can. Let's bring the class up here. All right. All right, so there's a few things we're going to do today. I don't need this open anymore. The first thing I need to make a note of is ABET. All right. Some of you are pretty new to the university, but ABET is the governing body that gives your degrees value. Okay, so there's some kind of governing, I don't know what to call them, some group of people that say UNLV degrees are valuable. In order to do that, we use a process called ABET, which validates that things are being learned and taught. So some of you have probably taken some ABET assessments before. On Thursday, we're going to take this assessment. It is not for a grade. Okay. Please come on Thursday. I will be ending class early for the quiz. Okay. So please come on Thursday. I will be ending class early for a quiz. It's only going to be open for a short amount of time. Because it's not for a grade, you don't have to look things up if you don't want to. Okay. I would prefer that you don't, because it is ABET. So if you don't know it, please just do that. I won't be submitting your names with the ABET kind of submission there. So I'll just take your grade, and then your name will be omitted from that. It's just to show that I did hopefully a good job teaching you guys, and if I didn't, I need to talk about how I'll improve next semester. Okay? Now, there are just a few things that I did not teach you. So we're just going to talk about those real quick. There's only 3 things. The first thing I want to talk about is in C++, there's a compilation process. I always forget this. If you want to read about it, there's a good link for that. Okay. But what happens when you try to make, say, an object file or code, an executable from C++, there's a few things that happens. The first thing that happens is the compilation process. So this basically is just running through your code, checking syntax, and generating some code. Okay. The next thing that happens is linking. Okay. And what that does is that's going to link in other files that are maybe libraries that you've included. And then the third thing that happens is you can execute your code. So you might see a question about this that says, what is the order of like the compilation process, or from start to finish? How do you create an object file? Okay. And these are the steps for that. And that's the exact order of them. So take note of that. The second thing I want to talk about is just these fancy words here. I don't use them. I kind of did maybe, but you'll see maybe accessor and mutator. What's a mutator and what's an accessor in maybe Mr. P terms? Can anyone tell me? In Mr. P terms, what's the accessor and what's the mutator? A getter and a setter, right? Specifically, what do we use in C++ to specify the difference between those things? Specifically, what in C++ do we like put? What's the keyword or whatever? Yeah, const, okay? That's exactly what that's talking about. So if you see that, it's talking about an accessor. Accessor is a const function. I know you can't see the screen right now. I'll bring that up. I'm sorry. And a mutator is a non-const function. Okay? So that's that. And then there's one more thing. Okay. There's one more thing that we need to talk about. Okay. And the last thing is when we do our own user-defined types, that is maybe structs or classes. When using user-defined types, structs, or classes, how much memory is allocated for each object? Do you guys have an idea on what this is? I'm accepting general answers, okay? But what do you think here? Is it set in stone? Is there something we can kind of use to estimate it? Do you have any ideas here? Yeah, however much it needs, I think that's a reasonable answer, yeah. It depends on a few things, all right? It definitely depends on a few things. The amount of... Yeah, so you can use size of, right? You could use size of to check. If you want, but in general, it depends on the variables inside of it. So pretty much whenever you declare a struct, pretend it's got, I don't know, a double, just as an example. It has maybe a double, which is 8 bytes. And then maybe a float, which is 4 bytes. So you might guess that your struct would take 12 bytes, right? So that's for the data. But in addition to that, there's a few other things it needs. It stores some information about the struct or class, such as like its type. It also has pointers directed towards the functions in there. Towards class functions. Okay? So when you look here, you don't always know exactly, but you're going to say 12 plus bytes for this. Okay? It's going to have more than 12 bytes, all right? At least 12 for the data, but then there's some information about the struct and the class. In addition, there's pointers directed towards the class functions. When you call a function, it needs to know where to look to find that code. So, these are the 3 things we need to talk about. A good answer for this question would be it depends. Okay? That's kind of my favorite answer. It depends. But you can always use size of to check. Are there any questions on this stuff? Obviously, it's not like crazy. Wow, I can't believe I didn't know that. These are just kind of some administrative things, I guess. So let me know. You're going to have some notes for that. Please come on Thursday, at least just to take it. I'll kind of open it up. If you don't want to listen to me that day, I guess you don't have to, but that's that. Now, today we're going to learn about our last thing. This subject is not very hard. It's rather just a data structure that you need to know before you go into CS 302. So we will spend some time on this today, but before I get into that, I vote we talk a little bit about our assignment. What do you say? I do see Fuzzy has a question, so I'm going to repeat this. I've already said this before, but we have one more assignment. I will be posting it likely tomorrow, okay, or Thursday, one of those days. It will be your last assignment, and I'm going to give you as much possible time as I can. All right, I'm going to give you as much possible time as I can. So that would be probably due date is going to be Sunday the 12th. Or Monday the 13th. That is after the semester has ended. My grades for you guys are due on the 14th, I believe. So I'm going to give you as much time as I can. All right, it is a final project, but I wouldn't say it will be harder than the linked list assignment or even maybe the musical chairs assignment. I think those 2 assignments, perhaps even the dynamic array assignment, those 3 assignments have been kind of rough on some of us. I wouldn't say that this assignment that's coming up will be any harder than those. Okay. I would say your linked list assignment is likely the final boss. And then the final project is just kind of like phase 2 of that. Yeah, linked list is a hard one. So that's coming up, okay? But like I said, you'll have plenty of time, I promise you. I'll make sure that, I know you guys have finals, so I'll make sure you can do it, you know, on like a Friday or something if you need. So that's that. Are there any questions on that? Let me know. Now, link lists, we pushed it back a day, and there are some issues. I know a lot of you are figuring it out, but some of you are not. In particular, are we having issues with any functions that you want to talk about? I may be willing to put one in front of you today if it's going to help you guys out here a little bit, but I do want to get some information on that. Chef asks, how does it decide who wins? There's 3 cases. If you look at the sample outputs, there's 3 different cases that it can end. One is someone runs out of cards. That is, they put their last card in the pile, and then the other player wins. And so one player ends up with all the cards. The second case is that it just went on too long. All right, the players got bored. So there's that case where they just keep going back and forth. After like 1,000 turns, they say, I'm done with this. And then finally, the last case is the game ends in a draw, in that one player runs out of cards during a duel. So there's 3 different ways that happens. Operator equal, the assignment operators that we're talking about, and swap cards. So if you're all okay with that, we can talk about those. Okay. I may not completely code them, but I'll give you maybe most of it. So you okay with that? And Chef, you can come to office hours, I think, as we discussed. So let's talk about those 2 things, beginning with the assignment operator. So let me pull up Visual Studio Code here, and let me go to our lessons, and let's look at our linked list code here. All right, so this looks similar to your deck class, as I'm sure you guys know. A lot of you have been copying this pushback function in, which is great. Perhaps this one as well. Now, let's take a look here. We've done clear lists. We've done some constructors. Let's go ahead and do the copy constructor and the operator equals. All right, so let's begin with this one. Now, this one is easy, right? But it depends completely on your other function, right? The operator equals. Let's see here. All right. So many of you did this, where you take the this, you dereference it, and you set it equal to the copy, right? Now that's the easy trick. That calls the operator equal function. Except some of you ran into some issues here. And that is, you forgot to initialize the head and the size of the deck. Now, why is that a problem? Well, let's get into it. Let's go ahead and pull up the other one. I guess I'm just going to copy this. Template type, this will be a void. LL type operator equals, and what does it take? Well, it takes this parameter, right? And if you follow my instructions, you notice I say something like call clear list here. Whoops. Right, because there's 2 different things that go on here. One thing to note here is that whenever this code shows up, or whenever this operator equal is called, that happens in main somewhere when we say something like, did I only declare one? So that happens somewhere in main here when you have your 2 linked lists and you say, hey, linked list 1 equals linked list 2, right? So that's what calls our operator. Now keep in mind here that linked list 1 at this point in time is already alive. All right, linked list 1 is alive and well. It was declared up here. This is where it was birthed, right? This is where it became something. Now perhaps this one was initialized with the copy constructor. That's fine. We can go ahead and pass in just a linked list there. This calls our copy constructor. And then this one here calls the operator equal. Now, what happens here is that since linked list is already alive, we probably need to deallocate some stuff that's going on in here. All right, and that's why we call clear list to begin. All right, that's why we call clear list to begin. We say, hey, let's go ahead and clear out this list real quick to make sure that we start from scratch. So if you call clear list at this point, you have to go up and look at that function. And up here, you'll see that I've got some stuff here. And then I say traversal node equals head. And I say while traversal node does not equal null pointer. This is where sometimes you guys will get seg faults. Or you'll get invalid reads. And it will say conditional jump depends on uninitialized values. Why is that? Well, in your copy constructor, you never initialize the head. Recall, there's a head here, and you're supposed to say something like head equals null pointer, and size of deck equals, I guess I just call it size. Size equals 0. Now, if you forgot to do that, they contain garbage values. Am I wrong? They contain garbage values. And so the first thing you do is call the operator equal. And then that first thing it does is call clear list. And then you get to that while loop. And at that point, this has not been initialized. I say traversal node equals head. Well, head contains a garbage value. And then I say while garbage value does not equal null pointer. Here you get an invalid read. Here you get an invalid free. And then your program seg faults. Does it make sense? So if you are doing this in your assignment 9, make sure you throw these in here. Okay, we have talked about that before. Now, here we are in the operator equal. You've cleared the list at this point. You've cleared the list at this point. Now you need to get started on making a copy of the other side. Well, the first thing you might want to check to see is if that copy actually has any elements in it. And if the copy doesn't, at this point you can probably return. Is the copy list empty? And if it is, then you're done, right? I think that's fair. Otherwise, the copy has elements. We need to deep copy. Now this is where things get rough, and this is why I recommend doing a pushback function, okay? Because there's a hard way and an easy way. Let's begin with the hard way, and then I'll give up probably halfway, because I am not going to have it, all right? So, at this point, the left-hand side is empty, and the right-hand side is not. This is the copy, right? So we need to traverse something. Which side are we traversing? Which linked list are we going to go through? How do we initialize it? Obviously, I need a traversal node. What do I initialize that to? What do I set it equal to? I think I have to make this a type. The copy head, yes. The copy.head. That's where that goes. All right? So that's your traversal node. Now, here's a problem. You need to be able to traverse that one. You also need to be able to traverse your own list. All right? You need to be able to traverse your own list. Now we'll get into that. But at this point, we know that we at least have a head on the other side. So why don't we say something like this head? I'm just using this to tell me the difference. Equals new node type. All right. We know that there's a head, and we can do a few things, right? We can say something like, well, let's put the card in there, right? So we can say something like head data or card is equal to the copy.head, or if you would prefer, probably the CT node data. Okay? So this copies the data. That's a deep copy. And then you probably want to do another thing. What is that? At this point, what do you want to do? There's something here that some of us are running into. If you run val grind, it will tell you your clear deck has issues here. As soon as I allocate this node, what do I want to do? Sure. If you want to do that, that's fine. I might do this instead. Kind of makes things a little bit easier. But if you want to, yeah, that's fine. But what I'm talking about in particular here is you don't know if this list has more than one element. Is it just one element? Is it greater than that? So at this point, you should probably say this. You may add something to it, that's fine, but there may be a case where you don't. And if you don't do that, then you're going to have the next, it's going to be pointing to some garbage value. And then what happens there? Well, let me make sure I kind of already got something pulled up here. So look here at this list, okay? Pretend you call clear list, and let's say you never initialized this next pointer to be pointing at anything. So in clear deck, you're going to be traversing through here. You're going to say, hey, I have something here. Let me save the next pointer. I'll delete this. I'll move here. Save the next pointer. I'll delete this. Move here. Save the next pointer. Delete this. Move here. Now you'll say, does this equal null pointer? Well, it's a garbage value. No, it doesn't. So what do you try to do here? Well, you're going to delete something that you're not supposed to be deleting. Right? You're going to try to delete whatever this is. And then you're going to keep traversing. At this point, your program will segfault. So you need to initialize this just in case. Be safe here. Make sure it's pointing to null pointer. Now at this point, you got to do something. While CT node next does not equal null pointer. Well, then what do? CT node equals CT node next. So move the copy traverse the copy list. And then what's the next thing you need to do? Well, probably, we need a traversal node for this list. Do you see where this is getting nasty? Didn't I tell you this one would be hard? We're going to have the CT node for the copy traversal. And then here we're going to have the TT node for the this node, right? For this list. So that's going to maybe equal the head. This is this traverse. So at this point, you got to say TT node next equals new node type. And then what? You've got to copy the data. Maybe you want to move it first. TT node, stop doing that, please. TT node equals TT node next. Move it over. And once you've moved it, then you say TT node data equals the CT node data. I probably forgot a pointer up. No, I didn't. So this is the deep copy, right? You allocate more memory. You move it. Then you copy the data. And then the next thing you should say is TT node next equals null pointer. And then that while loop will continue on. Right? Because this will move already. So there's going to be no infinite loop here. That'll move. You allocate memory. And then you move to the new allocated memory. You copy the data. And then you initialize your next node to be null pointer. This while loop will continue. Now, look at all of this nasty code. Are you guys having fun yet? This is why I don't recommend doing this. Even right now, I don't know if this will work. I have some ideas, but maybe not, okay? There's a lot going on here. Imagine debugging this, right? There's a lot of stuff going. Look at all these arrows. Look at all these news. I'm not having a good time. So what did I say? Let's get that pushback function going on. What does that do? Well, that adds a new node to the end of the list. So what I could probably do here is scrap this. All right, if you want to use this code, just watch the YouTube video. I'm going to delete it though, because I don't like it. I don't like it at all. So we'll keep that CT node, but the head is going to go away because I don't want it. And then I'm going to scrap this stuff too, except for the CT node next. You know what I'm going to do here? I'm going to get rid of this CT node thing here, and I'm going to say, hey, push back. If you want to say this to kind of make sure you know what you're talking about, push back, CT node, card. Look at that. If I get rid of these comments, look how small this function is. Wow, that's it. So what do? We clear our list. We wrote a function to do that already. Clears out our list completely. And then we'll check to see if it's empty over there. In fact, we don't even need this anymore. This could go away. Because if CT node equals null pointer, then we're not going to push anything back. So this could go away too. And then what do you have? Copy the size. Well, actually, we don't want to do that because pushback will increase our size. So I don't even think we need this because clear list will make sure it's 0. So what do we have to do? Clear the list, get a traversal node for the copy list, and then while it's not equal to null pointer, add it to our deck using the pushback function. Make sure you do the card here, not the card, but the data. Depends what list you're working with. And then traverse it. Are there any questions? Is that helpful to some of you guys? I'm seeing maybe Uchu, Synthos. Does that answer your question? I gave you the hard mode and kind of the easy mode, right? There's both. So that's kind of what's going on there. All right. Yes, you're welcome. And recall this push. I gave it to you. That doesn't mean you should not. That doesn't mean you can omit what's going on in there. You should know what happens in here. Okay. We talked about this. This is pretty simple to follow. I pretty much took all the code that was in there and I moved it into this pushback function, right? It all happens in here. So now we'll talk about swap and then we're going to move on today to the stacking queue stuff. Now there's probably a sort function in here somewhere, but we're not going to worry about it. But let's go ahead and add a swap. What is it swap? Well, it's going to swap two nodes, right? I think I named it A. I think I named it B. Now, I gave you a ton of this code in the Discord already, all right? So, I may finish it, I may not. We'll see if I'm feeling generous today. I don't know if I am. I have so much work to be doing, though, so I may save myself a ton of office hours if I just give it to you, but maybe it'll be nice, maybe I won't. Let's see how far we get. I'm just teasing you right now. It's not very nice of me. My main goal here is to make you understand this, okay? Not to just give it to you. I know a lot of you like that, but I just want to make sure we know what's going on. When we're trying to do something like this, what steps do I take to accomplish this goal? So what I said here is we're going to do the easy one, right? Extra credits up to you if you want to do that. Let's do the easy mode, in which nodes are adjacent. Okay? Most of the examples help, right? But this is the exact thing that's going on here. Anyway. Nodes are adjacent, okay? This is the easy mode. So A and B are right next to each other. Now, that doesn't mean A is always the left and B is always the right. That is not the case, okay? That will not happen. Let me prove it to you real quick. I'm just going to show you. If you want to match code grade, I'm going to ask you to put this shuffle function in here. And here's where the swap cards function gets called, okay? Now notice, this is a ternary. I know to this day some of you don't understand, but what does this mean? This is basically saying I2 will either be the card to the right or the card to the left. What does that mean? Well, that means that this could be to the right of the I1 or to the left of the I1. So, you cannot assume that A is always left and B is always right. You have to kind of figure that out first. So what do I say to do? Well, you need some node types, or just nodes in your assignment, right? There's no templates. And I say get your left node, get your right node, and then you're going to need this left previous guy. Okay? Now you may want to initialize them. That's fine. Just got an Australian accent going on here for no reason. So, we get these going on here, okay? I've been watching an Australian cooking show. That's where that came from. Sorry about that. Love those cooking shows. So, once we have this, we have to find them, right? This left and this right are here specifically so that we can generalize our code. In that I don't want all these if statements to say if A is greater than B or something like that. I don't want that, okay? I want to generalize it. So pretty much, what do you get? Well, you're going to say traversal node. We need a traversal node, right? That's a requirement. You need that. Just use a new variable to record the location. That's what we're going to do, right? So we need a T node here. It's going to point to our head. And then we're going to prepare to go through the list. You should go through the list to find which one's the left, which one's the right. So all you have to do is while T node does not equal null pointer. All you have to do here is say if T node equals A, then the left node equals A, right? In this case, you found it first. I know I'm kind of speeding ahead here, but we found A first. The left equals A. We know the right equals B. There's no point to look for it. We know that. Okay? We know that. And then we should break out. We're done. Okay? Then we're going to have another if statement here. If T node equals B, that means we found B first. So what do we say? Left equals B, right equals A. Yes, I am making aliases, and that's why Clang Tidy would give you all F's for this. But it's a linked list, so we have to get dangerous, all right? We live on the edge here. Otherwise, if we didn't find any of that, T node equals T node next. Any questions about this? We made some general variables. We made a traversal node to point to our head. And then while T node does not equal null pointer, let's see, is this equal to A? If it is, left is A, right is B, get out of the loop. If T node equals B, the left equals B, right equals A, break out of the loop. Else, we found none of them. Let's move to the next one and check again. At this point, we have a left and a right. Do you agree? Those will have values in them. Of course, if you want to do some checks up here, I won't blame you. You might say if, head equals null pointer, or if A equals B, that's fine. I don't mind. You can just return out. Because you're not going to swap those. There's nothing to be swapped. So at this point, we know that left and right exist. Now, what's the next step? What do I say to do? What did I tell you to do in the Discord? What's the next step? I'm taking a suggestion box here. There are two cases. What are those two cases that we have to consider? There are two cases here. What are they? If the left is the head node, right? Or the left is not the head node. Those are the only two cases that matter. Some of you might say, well, what if the right node is at the end of the list and it's pointing to null pointer? That doesn't matter because it'll be accounted for, all right? You'll see that. So, first thing you should do is, hey, does our left equal head? If so, do the swap code. I gave that to you in the Discord, so I'll let you fill that in yourself. Else, it's not. We have to find the left previous. What does that mean? T node equals the head while T node does not equal null pointer. We're going to traverse it. If T node next equals A, not A, left, then what? The left previous equals the T node, and you break. We're done. Else, the T node needs to go on to the next one. Start at the head to traverse. While it's not equal to null pointer, check to see if its next pointer is looking at the left node that you already found. And if you did, make sure you assign it, break out of the loop, we're done. If we didn't find it, move to the next one, try again. Now you could do some fancy footwork up here, and you could probably find the left previous somewhere in this while loop. Okay, you could probably do that too. Here I'm doing it inefficiently, I'm finding it afterwards, but that's fine. Now once you find it, at this point you know that you have these things. So what do? Swap the nodes. I gave that code in the Discord, right? So you either swap it if the left equals head, there are 3-pointer updates here, or down here you have 3-pointer updates. Now I'm just going to make note here. At some point you might say that the left next equals the right next. Well, guess what? If the right node was at the end of the list, this essentially it's just null pointer. So in that case, you don't have to consider it. It gets handled for you. And that's it. Any questions on that? You can fill in the rest here. Now, some of you are kind of smart. A lot of you are smart. You can use this too. If you find, say, the left node at index I, well, the left previous node is at index I-1, right? So you can use this here, right? You could save the indexes, and you could say, my left previous is at I-1, left is at I, and the right is at I+1. So you can try to use that too. Any questions on this? Or are you okay? And do you think we can get this done by tonight, right? Let's get it done. Let's get it turned in. Let's get our points. Let's pass our class, right? We all okay? Please let me know if not. I'm not going to test this because if it doesn't work, then I still want you to figure it out because I pretty much gave you this, all right? It's pretty much good to go. Don't give me these sad faces. We've got to be positive. We've got to smile. We got to say, we're going to be good coders someday. And we have to suffer now so that I can make money in the future. Okay? We suffer now so that we can make money in the future. Or we can help people. One day I would love to continue teaching, or I would love to write code in healthcare or something. Okay? Yes, absolutely. Someday is not today. But someday we will be good programmers. So you have to suffer now. Okay? You have to suffer now if you plan to be good later in life. And then someday you'll be like me, where students will message you questions about how to swap nodes in the linked list. And you'll be like, well, you obviously forgot to find the left previous node. All right? So we got to get there somehow. So please give this a shot. I'm available, okay? So just message me. I mean, I'll be working on my own projects, so you might not get a response, but I'll do my best. You better remember it for the rest of your life. All right. Excuse me. So, now that that's done, let's talk about stacks and queues. These are pretty simple. All right. Oh, I think I can't believe I did this. I think Top Wolf asked me when the final exam is. Does anyone know? Let's go find that. I'm sorry, that skipped over my mind. All we have to do is go to final exam schedule. UNLV Fall 2021. Calendars and schedules. Final Fall 2021. Looks like Giovanni wrote that down there. Take note. Mark it on your calendars. What are we? We are a Tuesday, Thursday class. We are a Tuesday, Thursday class. When is our class? It is between 11:30 and 12:59 p.m. So Thursday, December 9th, 10:10 to 12:10. Thank you for that. Write it down. All right. Make an NFT of the clip. Do it. Someone clip that. I'm just kidding. So, I might put this on. I think you guys might like me to put that on Web Campus, so maybe I'll do that. In the meantime, let's move on, shall we? A Mr. P NFT. Man, Chef, you're going to have a good day. I'll tell you what. I will upload. You guys have the review. I'm going to upload even more review for that stuff. Final exam is cumulative. It will have a little bit more questions, but it will be about the same size as test 1 and test 2. But it's cumulative. So what does that mean? We're not going to have 8 questions on pointers. We're just going to have 4 questions on pointers. Does that make sense? So you have less questions in each section, but you're going to have questions about everything. Same format as the other tests. All right, same format. 2021, 11:30. Stack and queue. What's something you think we might struggle with on the exam? It's always the programming question that gets you. Not you specifically, but everybody. Any coding question kind of gets you guys sometimes. I asked you some of the recursion stuff. I know you guys are kind of crammed, and it's kind of hard to think about some of these things. The final exam will not be as time constrained like the last 2 exams. You're going to have 2 hours to do it. And I think I'll even give you the extra time. So you won't be as crammed. So you'll have more time to think about things. But definitely coding is a pain in the butt. Yeah, Chef, I agree with you. Coding on Canvas is not... It's not a good time, but this is what we're dealing with right now. You know what I had to do in my undergrad? I wrote the programs on paper. So I don't know what you prefer, but I did not like writing code on paper. You tell me what you want to do, because either way, they're not good. Yeah. Program on paper. That's great. I had an awesome time with that. Oh, I also want to commend you guys. I've been running Moss on all the assignments. I'm not finding it much similarity between that, so I do commend you for working on your own programs. Thank you for not cheating, because if you were cheating, I would have found you by now. All right, I'm very grateful for you guys not doing that. I hate sending that message. I hate submitting you guys to student conduct, so thank you for doing that. Fuzzy asks, yeah, if you want a text document, I understand that. I don't know. I wish CodeGrade had its own text editor, but not CodeGrade. Lockdown browser. I wish it had a text editor. I'm not sure if it does. Fuzzy asked, did they have to scribe code on parchment? Yeah. Does anyone know how coding was done back in the day? Does anyone know that? Tell me, how was coding done back in the day? Someone's got to know. I know that some of you guys probably have parents that did that. You'll at least hear it for some of the professors. Sticks and stones. Spoken word. Carrier pigeon. Ah, moldy. Yeah, that's right. They're punch cards. Or they're like bubble sheets. So instructions had like a line of bubbles, and pretty much you would take a card and you would either punch it or you would mark it with a pencil, and that would be the instruction. And then you feed the punch cards to a computer, and it reads them. You had to make sure that you wrote. You had to write page numbers on your punch cards because programs might be 100 or more punch cards, and then you're running through the hallway and you get hit, and they all fall on the floor. And if you didn't have page numbers on them, you were screwed. Now, Fortran was the first programming language. I don't know about that, Fuzzy. It would take more time for me to grade it too, so. Anyway, let's get started with this. We're sidetracking. By the way, last 2 classes, so get your Mr. P time in now, because after Thursday, you're not going to see me. Well, you might see me again, but never in a CS202 format, so make sure you enjoy these last moments, because I know I am. Okay. So, stacks and queues. Let's talk about that. Can anyone tell me what a queue is? Another word for queue. Think the United Kingdom, Britain. What's another word for it? I think Synthos is closest. Uchu's the one I'm looking for. It's a line. It's a line. So what do you do when you go to the DMV? You wait in line. When you play League of Legends, what do? You hop in the queue, right? When you play Overwatch, what do? You hop in the queue. So in the United Kingdom, they call lines queues. All right. Nick, it's up. I'm a graduate student, right? I'm not an assistant instructor here yet. I may be someday, but I really just get thrown wherever they put me, so I can't tell you. Did we die? I'll take a water break. Are we back? I'll take a patty break. Y'all gotta tell me when I'm back here. All right, guys. Another word for queue is a line. Now, a stack is a little bit different, okay? A stack is like a line, but it's a stack. Nick, I said, I'm not sure. I don't know yet. I've taught 202 for 4 semesters. I've also taught a database class. So I can't tell you yet, but we'll see. By the time I'm an assistant professor, if I am, you guys will be long and gone. So unless you're telling your much younger children, not children, but siblings, I'm not sure yet. A stack is like a line, except it follows a different rule, and that is FIFO and LIFO. So can anyone tell me what FIFO and LIFO stand for? What are those things? What is LIFO and what is FIFO? Thank you, Zinthos. I appreciate that. All right, LIFO is last in, first out. Okay, and FIFO is first in, first out. All right, that's a test question right there. What is the difference between a stack and a queue? What do these things stand for? Test question alert. Test question alert. All right? LIFO and FIFO. What do these things stand for? It's that. Now, what does that mean? Well, a line or a queue is first in, first out. Let's say I was the first one to get in line. That means I'll be the first one to get my burger at In-N-Out. Okay? I was the second person to get in line. I'm the second person to get my burger at In-N-Out. Okay? Not a huge deal there. LIFO is a little bit different. I like to call it an unfair queue. Okay? It's unfair in that, let's say I got in the stack at, In-N-Out, and then someone got in front of me, and then they got their burger first. Okay, so stacks are unfair, at least with people. When it comes to many programming problems, stacks are very helpful. Okay, stacks are exceptionally helpful. Yes, that's a great example. Let's go ahead and do some examples. A queue example and a stack example. Queue example is line at In-N-Out, right? In-N-Out. I don't know how to spell it. I'm sorry. What's another example of a queue? Queuing up for League of Legends, right? Or a game. All right, DMV, stuff like that. Now, a stack example is exactly like that, all right? A stack of plates. In a stack of plates, which one went on first? The bottom plate was placed first. But it will be the last one to be removed because you can't get to it by taking... You can't get to it until you take off the plates on top of it, right? You cannot get to the bottom plate until top plates are removed. Okay? Additionally to this, this is like a web page or an app. You want to know how the back button works? When you go to, say, some website that, you know, that's not full of ads and things that don't redirect you, what do? You say you go to walmart.com and then you click on products and then you click on clothing and then you click on clothing for men. You've made a stack of 4 things. Walmart on the bottom, products on top of it, clothing on top of it, and then clothing for men on top of it. And then you hit the back button. You take this one off. Now you're back in clothing. You hit the back button again. Now you're back in products. You hit the back button again. Now you're at walmart.com. Does that make sense? Stacks are used on web pages or apps. Stacks are used in your programs. In computer architecture, actually. Architecture. Someone tell me if I spelled that wrong. Very important for function calls and recursion. Yes, that's a stack. That is a stack. Okay, so do we understand that? Okay, hopefully we do. Now this is the last little bit of stuff here, and then we're done with the notes. Wow, that was hard. Amazing. 3 functions. So first thing we'll note is stacks and queues are like dynamic arrays. Your favorite, all right? So what does that mean? Well, they can be implemented using linked lists. You can do it contiguous arrays, etc. All right? They're like dynamic arrays. What are you doing? You're storing multiple elements in a line, right? In an array. But the order matters, okay? So these could be implemented in any kind of way. I think maybe when we get to the last assignment, I'm going to allow you to implement a stack and a queue with either of these. I think I know which one you'll pick. I'm guessing it's this one. But if you want to, I'll let you do the linked list implementation. It won't bug me. Maybe I'll offer an extra credit opportunity there. I know some of you like that, especially now that we're coming up on the end of the semester. So stacks are like dynamic arrays. Now, you can only access one element at a time. And what is that element? That is the element at the front. That's either the element at the front of the line or the element at the front of the list. You only have access to that one thing. What does that mean? No sorting. No going through your list and looking at things. Okay? You can't do that. These are very simple data structures. How do we store the data? We put something in the line and then we take something out of the line. That's it. All right? You can only see the element at the front at any given time. You can't get to the things underneath it. All right? You can't do that. So there's three functions. Function 1 is what's called push. Where does that push come from? Where have you heard this before? Where's that push come from? What does that mean? What does that mean? Someone tell me. Where does that push come from? Push is on the stack, or in Q is in the queues. Push back, right? Push back, push front. What are we doing? We're putting something in the line. What does this do? This adds an element into the stacker queue. Put something in the stack. So push some item, right? Or in queue some item. All right. What is the type of this? Well, it's probably a void. Right? It's a void function. So what does it look like? It'll be like void, push, some type, item. Okay. Now, the next one, pop. That's the stack. What does that one do? Or DQ. That's the queue. What does that one do? Pop, right? Yeah, Top Wolf's ahead of me. What does that one do? It's pretty easy guess, right? What's the opposite? Takes an item out, right? Takes the front item out, okay, and returns it. In some sense, your linked list assignment right now, remove top card, that's like a pop, right? You're only taking the top card off and you're returning it, all right? So it's not a void function, but it is returning some value, returns an item. Thus, you probably have some type here, pop that, okay? Notice that, I just pressed insert. Notice that this one here, it takes an element, right? The one you're gonna push in. Notice this one here doesn't take an item. You're just gonna take it out and return it. Now, there's a for fun function. Okay, here's a for fun function. Peek. I like peek, all right? I like peek because maybe you wanna see what's up top, all right? Maybe you wanna see what's up top. So peek can be used in stack or queue. And what is this? This just looks at the, kind of looks at the front. You'll see this sometimes, okay? You'll have a peek, it just looks at the front. It may return a copy of the item, does not remove it. Okay, so what does that look like? Well, it's gonna be type peek. Right, because it's gonna return a copy of some item. So these are our three functions that you usually see. These two are imperative, or I don't know if that's the right word I want to use. These two are required. In every stack and queue you'll ever see, they have these two functions. Now this one might be available for some, but not always. This is kind of just for utility. So that's it. So what do you say we make some pretty pictures, and then we'll maybe do some code next time. Maybe we'll end class a little bit early today. I don't see why not. So let's make some pretty pictures here, and we'll get going. All right, step one. That's not what I wanted to do. Step one. Goodbye. Step two, Control-Shift-I. Step three, let's make the background dark, and let's make the foreground, I don't know, light blue. Okay, let's go ahead and start with our cues. What do you say? Cue. All right. Now, what do I like to imagine a cue as? Well, I like to imagine it as kind of two parallel lines together. Two parallel lines, okay? So this will be our cue. And they're open on the front and on the back, okay? They're open on the front and on the back. So if we're going to call anything here, the front and the back, we're going to call the top the front of the line, the front of the cue. And then down here, we'll call this the back of the line. Okay? And what is the direction of items here? Well, items will go in through this way. Let's make this red. Nice arrow. Nice job. Wow. So when you call NQ, what happens? Well, they go in this direction. So that they go behind whatever elements are already in there. And then when you call DQ, they come out this way. Okay? So that's the DQ up there. Pretty simple stuff, right? It's not like we're learning rocket science here or anything. So the NQs go on the bottom, the DQs come out the top. So let's kind of visualize this a little bit. Let's make some pretty faces. I don't know, these guys might be happy or sad, I don't know. That's the average Mr. P student right there, right? Always smiling, never mad or anything. That's the average Mr. P student. Smiling. There we go. So, what happens here? Well, let's say we NQ somebody. So what do? They go into the parallel lines and they move all the way up to the front. Now, maybe they're going to be waiting in line, right? So what happens next? Let's say you call in Q on somebody else. What do they do? What do they do? They go up here. They get in line behind that, right? Then you call in Q again. What happens? They come on down through here and they get in the line. Now, finally, I'm ready to call DQ. Now I'm ready to call DQ, right? Yep. You hop in line for office hours, right? Maybe you go in with a sad face, but then you come out with a happy face. Now, this person was the first one to come in. Now they are the first person to come out. Right? And then this person moves up. They say, here, actually everyone moves up. Nice and slow. Nice and slow up the list here. There they go. Now they're ready to move on, right? And then you call DQ again. Who comes next? Well, this person was second in line. That means they're going to be the second person to come out. And there they go. So, does it make sense? Do we have any questions here? Now we're going to show you the stack. Now the stack is the unfair one. Recall that. The stack is unfair. Sometimes I do answer your questions like a stack. Sometimes an easy question comes in and I push one of you aside to answer someone else's question. That's not very nice of me. I understand. but you know how it is sometimes. It's unfair, all right? It's unfair. So what am I going to do here? Well, I'm going to maybe grab my lines as best I can. We'll slide this over here. You guys hopefully can still see that. I'm going to make it a little wider. Now, I like to think of this as a bucket, rather, okay? I like it to be a bucket. What does that mean? This is closed off. So no one can go in through the bottom, all right? No one can go in through the bottom. All right? No one can go in there. So what does that mean? Well, if you're gonna push onto the stack, if you're gonna push, what happens there? It looks like this. All right, that's our push function. They go into the bucket, kind of. That's our push. And then when we pop, where do they come out of? Well, there's only one direction, and it's this direction. So they come out through here too. So you go to Unfair Burger or something, right? You're gonna get your Nashville hot chicken at Angry Chicks or something. And say they're doing this unfair thing. Let's say they're doing this unfair thing. So what do? Maybe someone gets pushed onto the stack. Well, just like the plates, they go all the way to the bottom. And then you push somebody else. Well, guess what? They go on top. Now they're here. You know, now that I'm thinking about it, I want you guys to make sure that this is unfair, right? Said, hey, I got here before this guy. How come they're going to get served before me? So the person at the front of the line may always be happy until someone gets in front of them. So what do they get? They're going to get some. Now that's the average Mr. P student, right? There we go. That's what I'm talking about. So here they are, right? So then you call push again. Someone gets pushed back on top there, right? Now you call pop. Does this guy get to come out? Absolutely not. He can't go anywhere. I can't go here. I can't go there. I can't go down. I can't go up. I'm stuck. So who comes out, right? This one. Now I'm out. Okay? Now, who's next? You call pop again. This person comes out. And then you finally call pop again. And then this person is finally able to come out. Hard stuck on the bottom of the stack. That's right. Okay? That's how the stack works. Okay, that's how the stack works. So, those are the main differences. If you're going to visualize it, think of the line as like a tunnel, right? People go in through the back, they come out through the front. And then if you think about the stack, it's a little bit different in that people go in through the front and they come out through the front. So there really is no back here. There is just a front. I don't really know how to describe the back in this case because it's not accessible, right? There's only the front. The back is down here, but you can never get to it, really, right? You can never get to it. Giovanni, you're correct. Reversing a list easy. You just pop it out. Now, I told you last time with the linked list assignment. Yeah, the bottom. That's a good word for it. I told you last time, the linked list assignment, if you're going to do the easy mode of the operator equals, if you're going to do the easy mode of that, if you use add to top of deck, you're going to reverse all of the cards, right? That's why you have to add push back into that class because it works differently that way. Meaning you're going to be adding things to the back of the line, right? You're not going to be adding things to the front of it. So exactly what you said. If you call add to top of deck in your assignment equals or your operator, your assignment operator, you're going to reverse all of the cards, right? And that's exactly what happens here. Could the first element in a stack become the last element in another stack? Yeah, Synthos, that's possible. This line of code may exist somewhere. Stack 1 dot push stack 2 dot pop. We'll get more into that code a little bit later. On your final exam, I'm going to ask you what is the output of something like this program. Notice here we have two stacks. Stack 1, we're going to push on an element. And what are we pushing on? Well, we're going to take out the top element of stack 2. Okay. Now, what's an easy way to implement a peek function in a stack? That's going to be my next question for you. Let's pretend we're using a stack. Can we implement peek? Implement peek only using push and pop? You guys have any ideas? Well, so Chef says just do the pop but don't actually remove it. That's what the peek should do. Can you implement it by just using push and pop though? What do you think? How can we do that? Ooh, my face is here. What do you guys think? You think there's something we can do with that? Can we implement peek only using push and pop? Pop it out and push it back in. That's exactly right. Type element equals pop. I'm assuming that this is maybe inside of a stack class, okay? I'm assuming we're maybe in a stack class here. So I'm just going to call this pop or something, right? And then what do? I can say this, push the element back on top, and then I can return the element. You understand that? Does that make sense? So that's all I got for you today. Next class, we'll do a little bit of coding, all right? And I'll show you some examples of this stuff. I'll kind of ask you what the output of some code is. Just a few notes. Let's just keep this in our minds. All right. Let's keep this in our minds. Final exam next week. I think we said December 12th. No. That's not right. December 8th. December 9th. Whoa. December 9th from 10:10 to 12:10, right? I will have a final review posted very soon. On Friday, all right. Final project, final homework coming out on Wednesday or Thursday. Okay, this one's worth 200 points, by the way, so please get it done. And remember that this one may replace your assignment 1 grade if you do better. If you do better on it, it may replace your assignment 1 grade. Otherwise, if you don't do better on it, then I'll keep your assignment 1 grade. You remember I said that? I don't know what that's about. Okay? So final exam next week, final homework on Wednesday. Please come to class on Thursday. Can't believe you called me that. We have an ABET assessment, so I'll end 15 minutes early. Okay. All right. I might put this on Thursday as well. And also, final day to come see Mr. P, right? It's the last day. Sad face. So, those are notes, okay? Final exam coming up, final homework coming. Please come on Thursday. We have an ABET thing, and it's the last day you can see me. So Send me to the back of the stack. All right. So, thanks for coming today. I hope you learned something. I hope I was helpful to you. And I hope that you can get assignment 9 done by tonight. If not, tomorrow, the late deadline. You know I'm pretty reasonable on that. Just send me an email or Discord message. I will have office hours. I've got a line going on. So I'll send a few of you some messages just to let you know where you are. I hope you guys have a great rest of your day. And I'll see you guys hopefully on Thursday. You're free to go. I've got a queue. That's right. I've got a queue. The Mr. P season finale. You're funny. Yeah, have a great day. I'll see you then. You're welcome, Nick. You're welcome, Top Wolf. You are welcome, Chef. Uchu, you're welcome. Thank you for that. Synthos, you're welcome. Cade, you're welcome. Giovanni, you are welcome. I'll see you next time. I guess that's what we got. Yang, you are welcome.